Hi, my name is Greg McFarquhar. I'm the director of the Cooperative Institute for Mesoscale Meteorological Studies and a professor in the School of Meteorology at the University of Oklahoma. I was born in Toronto, Canada, and I did all of my schooling there as well. I did my undergraduate degree in physics and mathematics at the University of Toronto. And just by chance, I got a summer job at the end of my sophomore year working at Environment Canada in Downsview, Ontario. And during that time, I developed a model of how a rain-snow boundary evolved. And that got me interested in atmospheric physics, so that when I started my graduate work, I decided to transition from physics into atmospheric science. And then I did both my master's and PhD in the cloud physics group at the University of Toronto, concentrating in studies of warm rain. After I finished my PhD, I realized that there was not a lot of opportunities for people who wanted to do pure cloud physics, but that there was lots of opportunities for people who wanted to look at the applications of cloud physics. So I accepted a postdoctoral fellowship at C4, which was the Center for Clouds, Chemistry, and Climate at the Scripps Institute of Oceanography. And during that time period, I started my career in doing aircraft measurements by making measurements of tropical anvils out of Fiji. After I finished my postdoctoral work in 1994, I joined the National Center for Atmospheric Research in Boulder, Colorado, and I worked there for 6 years as an associate and project scientist. After working there for 6 years, I decided that in addition to doing pure research, I also wanted to have the opportunity to mentor and advise graduate students and have my own research group. So in 2001, I accepted a position as an assistant professor at the University of Illinois in Urbana-Champaign, and I stayed there for 16 years working as an assistant, an associate, and ultimately a full professor. In August of 2017, I decided I wanted to do yet another transition, so I accepted a position here as director of SIMS and professor in the School of Meteorology, and that is where I am right now. I had never actually thought about studying meteorology or cloud physics until my sophomore year as an undergraduate. I was envisioning that I would probably be studying nuclear or quantum physics for the rest of my life, or maybe ultimately working as a computer programmer. But at the end of my second year, I got an opportunity to work on a summer internship at Environment Canada. And that was doing research on a rain-snow boundary and how it moved and evolved. And at the end of that summer, I actually wrote and published my first scientific paper, which was in Water Resources Research, that described the model we had developed. At the end of that summer, I was introduced to the man who would eventually be my PhD advisor, and I told them that I was uncertain whether I wanted to stay in physics or transition more into atmospheric physics and meteorology. The advice he gave me was to finish my degree in mathematics and physics, and then if I wanted to change to atmospheric physics, I would be able to do that as a graduate student. So that's basically why I had to study my path to studying cloud physics. And I just found this to be a fascinating field where I could take a lot of the raw training I'd had in basic physics and quantum physics, wave theory, nuclear physics, and then apply a lot of those techniques to something that was a lot more tangible or physical. And so that really got my excitement in cloud physics. And then the other momentous event that encouraged me to do my career in field campaigns was during my PhD studies. I decided that I might want to go somewhere else for my PhD because I had lived in Toronto my whole life. However, my advisor told me that if I stayed in Toronto to complete my PhD, he would give me an opportunity to go to a field campaign in Penang, Malaysia. And that was the first field campaign I participated in. And I had a great time there. I really enjoyed working with the ground-based probes and the aircraft. And so I decided that that was something I wanted to do for the rest of my life. So that was my first opportunity to do a field campaign. And I'm happy to report that I've now done 25 in my career and looking to do at least another 25 before I retire. Well, my research focuses on clouds, and the reason being is that if you look at some of the most fundamental problems that exist today in understanding both the prediction of weather and the evolution of climate is the fact that we have a very poor understanding of the basic properties of clouds, and because of that, we have a very poor understanding of the processes that are occurring in clouds and how that affects both weather and climate. So for example, right now climate models will tell us that the amount of warming by 2100 is projected to be between about 1.5 and 4.5 degrees Celsius. The reason there's a lot of uncertainty is because there's a very poor understanding of how to represent clouds in Earth system or general circulation models. And then in terms of weather prediction, we have a very poor understanding of quantitative precipitation forecasting. So for example, how much rainfall will be associated with a hurricane or a mesoscale convective system? Or how much snow will form in wintertime snowstorms? What will its phase be? Will it be sleet? Will it be freezing rain? Or will it be snow? In order to better predict all of this, we need a much better understanding of clouds and cloud processes. So in my group here, I have a lot of graduate students and postdocs working with me, and we're looking and trying to better understand the properties of clouds. So just like if you wanted to study a tree, and you wanted to study, say, a palm tree, you wouldn't climb up a mountain in Colorado and look at the tree there. You'd have to go where palm trees occur. So similarly, when we want to study clouds and different weather phenomena, we have to go where the weather phenomena are and look at the clouds in those regions. So what we do is we put a lot of probes and install them on aircraft, and then we take the aircraft and we fly them through clouds. And that gives us a lot of information about the numbers of cloud particles, the shapes of cloud particles, the sizes and their concentrations, and then our job is to use that information to tell us about processes that are occurring in clouds and how to better represent those processes in clouds and weather models. So just as examples of some of the phenomena we've looked at wintertime snow bands in the Midwest of the United States. We've looked at mesoscale convective systems over the Midwest of the United States. I've done projects where we flew over the Arctic Ocean, looking at the properties of Arctic clouds and how that impacts weather. We've done measurements of hurricanes, trying to better understand landfalling hurricanes and also how aerosols affect hurricanes. We've done projects where we've looked at tropical clouds and tried to understand the anvil shields that are generated from tropical clouds, how to represent those in climate models. We've done projects where we've looked and tried to understand the impacts of clouds on aviation, to understand what impact it might have on an aircraft as it flies through clouds. And our two most recent projects, one is looking at the impact of biomass burning aerosols that are occurring in Africa now, looking at how those affect the properties of clouds off the coast of Africa. And the next project is going to look at Southern Ocean clouds. Those are clouds between Australia and the Antarctic. And we want to do that in order to understand what are more pristine clouds, sort of pre-industrial clouds, and also to understand why there is so much supercooled water, that is clouds that are occurring at temperatures less than freezing. And we want to look at that and understand how that impacts both weather and climate models. Well, there are a lot of opportunities available for both undergraduate and graduate students in SIMS. And for those of you who don't know SIMS, SIMS is really a cooperative institute that takes advantages of the scientific technical expertise that exists at both OU and NOAA, and also the resources at OU and NOAA to do some fundamental research, say on things like radar, on storm scale development, to look at how extreme weather events are being impacted by climate, to look at how to better forecast extreme events, and also looking at the social and socioeconomic impacts of some high impact weather events. So there's a lot of resources available at SIMS. We have a lot of funding, and there's a lot of projects in those different areas for which there's lots of opportunities for both undergraduate and graduate students to get involved. So there's mentors both within the School of Meteorology at OU who are involved with SIMS, and then there's also a number of scientists within SIMS itself, as well as within NSSL, who can help advise students who wish to get involved in projects that are of relevance to the SIMS mission. Well, the one piece of advice I would have, and this applies to both undergraduate and graduate students when you're looking for an internship or a project to work on, is to talk to a lot of different advisors and get a feel for what their different projects are. And the key thing is that you find a project to get involved with that you find very interesting. Because if the project is very interesting to you, you will be able to do the amount of work it takes to make impacts on what you're trying to do. So really just choose something that is of interest to you, and that's the most important piece of advice that I can give.